Okay, I believe we can get started. People are still likely going to be trickling in, but good afternoon, everyone. I am Nicolo Floresca, the Inside Technical Sales Supervisor for the Filtration Division of John Brooks Company. Thank you for joining us today, and we hope that everyone is safe and well. This is part one of a three-part series that focuses on the compression and purification of ambient air and gases. Today's presenter is Zenon Gluch, the technical sales representative for the filtration division for Eastern Ontario and Western Quebec. Zenon is bilingual, so feel free if you have any questions to shoot him over in French as well. Zenon possesses over 25 years of knowledge in the field of compressed air and ambient filtration purification. His previous tenure was with Paul Filtration and SPXFlow Technology. Zenon will also be joined by Russ Ayres, the sales manager from SPXFlow Technology, who has over 35 years of field experience in compressed air and purification. Today's presentation will be recorded, and its link will be sent to you to share with your friends and colleagues afterwards. So a little housekeeping before we begin. There will be a Q&A icon at the bottom of your screen that you can populate questions, and we'll do our best to answer them. If we do not have time within the 1 hour limit that we've allotted, we will send you our answers afterwards. So thank you again for setting aside the time for this learning opportunity. And with that, I turn it over to Zenon.
Thank you, Nico. It's a pleasure to be presenting this compressed air. It's a basic overview of, moisture and different aspects of air that we live with on a daily basis. And I have the pleasure of having Russ Ayres accompany me. So we'll get straight to the presentation. Outline of today's presentation is the compressed air basic theory, the consequences of pressure, temperature, dew point, relative humidity, and then at the end we'll have some questions and answers. Since I don't have the pleasure of seeing your faces, and not being sure if all is clear, we would appreciate if you enter your questions in the Q&A section. As visualized in atmospheric air, there's always a certain amount of moisture. It could be in the form of clouds, a mist, or rain, but there is moisture even though we don't see it. And moisture is dependent on seasons, locations, climates. So depending where you're at, the moisture content will change based on the season, on the elevation, and would have multiple changes, specifically here in Canada, because we get the warm climate, we get the cold climate. So we do have large variations in the moisture content that we can experience on an annual basis. The following image is just to represent that, it takes approximately 7 cubic feet of atmospheric air to make 1 cubic foot of compressed air. And this has a consequence on the concentration of the moisture in the air. Typically in atmospheric air, we don't see the actual moisture in the air. We may feel it on a hot, humid day like it is here today in Montreal, but visually we don't see it. Once you compress it 7 times to get it up to 100 psi, the contaminants consisting of water get concentrated at that same level, 7 times more concentrated. So it may exceed the moisture holding capacity of the air once it's compressed to 100 psi, and the moisture goes from a vapor form into a liquid form. As illustrated on this slide, we see that, on the right-hand side, we see that there's approximately 3 grains of moisture per cubic foot. Once it's compressed to 100 psi, or this illustration is indicating 120 psi, so it'd be 7.8 times the concentration level. It may exceed the moisture holding capacity of that cubic foot to hold that amount of moisture. And that's when typically the vapor would change from a vapor into a liquid form. Basic knowledge is that as we compress the air temperature increases. The pressure increases, which is a normal factor. And the main factor that we're concerned about is that the contaminants in the air also increase approximately 8-fold or 7.8 times. Now, as shown on the previous slide, if we have 24 grains of moisture per cubic foot, some of that moisture will condense and turn into a liquid form. And that's when we have to assure that that liquid is not causing issues with the compressed air system. Basic knowledge, what we're trying to indicate here is that the dew point of air is basically the transition point when the vapor turns into a liquid, that the air can no longer hold that amount of moisture in the vapor form, and it's changing from a vapor into a liquid state. That's when the relative humidity becomes approximately 100% relative humidity, and we've exceeded the saturation point of the air, so it can't accept any more moisture. That's illustrated on the following slide. At minus 40 dew point, the air is relatively dry. I should take this back a little bit. At minus 40 dew point, the air is relatively dry. And this illustration is indicating that when you expand that air from a minus 40 dew point, 7 times larger to an atmospheric pressure, the dew point actually gets drier. As previously stated, when we're taking atmospheric air, which we don't see the moisture, and we compress it to 100 psi, then we get condensation, we get saturation. So now if you have dry air at a minus 40 dew point and you expand it to an atmospheric pressure, the actual air gets drier because now you have 7 times more volume to have that amount of moisture that was previously dry to a minus 40 dew point.
Hey, Zenon, it's
Yeah.
Russ here. Can you go back one slide for me just for a sec?
Yeah.
So I just wanted to say that, this weekend, we're going to have some higher temperatures than we've had over the last little while. So you'll be able to, if you think about dew point, you'll be able to see this in action. So if you go out in your yard and have a barbecue or something and take a cold beverage of your choice out there, as long as it's cold, we're going to have temperatures of 30 degrees C this weekend, at least where I am in Collingwood, and probably in Montreal, Toronto, and wherever in Canada. It's going to be a warm weekend. If you put that cold beverage on the picnic table, you will, spend 5 minutes looking at it and it'll be covered in moisture. And if you lift it off the table, it'll be a ring of moisture on the bottom of the table. What this is the air that contains, because of its higher temperature, it contains an elevated amount of water vapor. When it touches the glass, it drops in temperature and condensation takes place. And the vapor turns into liquid. So that's just an illustration of what we're talking about when we talk about dew point. So
that's a good point, Russ. And I was going to indicate, if the air, or since that drink or whatever component is that is in contact with the air is cooler than the dew point of the air, that's when we start getting condensation, and that's, like you stated, would cause liquid droplets to form.
So the dew point is actually important, as we relate it to, compressed air purification. It's important from the standpoint of, a customer may have certain processes and equipment in his plant, and it may not be able to withstand or operate properly when there's liquids present. So it's important to know what the temperature inside the plant is, or the temperature in the area that the facility is located. But it's also important to know what the dew point of the compressed air is, because you must keep that dew point low in order to protect that equipment.
Yeah, and that's why also, like I was going to mention, Russ, that there's, you know, with seasonal changes on a hot, humid day, if you compress your air, there's substantially a lot more moisture in the atmospheric air on a day like today compared to in the cold winter days, or if you're in northern Alberta, you know, over there it gets cold and dry, and even once the air is compressed in the winter time, you may not get saturation levels in the winter time compared to you would in the summertime.
Correct.
Yeah. The following illustration again is just to elaborate on, you know, the typical purification systems that are designed for instrumentation air. We try to attain a -40 dew point, and as dew point previously stated, that's the temperature when condensation occurs. So you would not get any water droplets or the formation of change from vapor into a liquid form until you descended the temperature down below -40 degrees Fahrenheit. Sometimes, you know, we get instances where, you know, Russ, you were indicating to me earlier this week that you had certain circumstances where people were assuming that they were getting good dew point, but they were perhaps reading an atmospheric pressure, and we'll see that a bit better, and you can elaborate that on the next slide. But this image is to further elaborate that a -40 dew point at 100 psi, once expanded to atmospheric pressure, since we have 7 times more volume, the actual dew point gets less since we're expanding that air to a lower pressure. And yeah, this illustration again just restates that a -40 dew point, I'll just try to get my cursor here. Yeah, -40 dew point at 100 psi is the same as a -70 dew point at atmospheric pressure. Similarly, you know, I was just thinking about this when I was going to give this presentation. If you're filling the air in your tires, or if you're, you know, painting your home, or, you know, it all has a consequence of the moisture content. So ideally, you shouldn't be filling your car tires on a hot, humid day, because then you'll have a certain potential of water formation inside your actual tires, even though you're only pressurizing it to 30 psi. But the goal is always you want to get compressed air source at the driest time possible, and this way there's the less likelihood of having liquid formation once it gets compressed 7-fold and is at approximately 100 psi.
So to give you, Zenon, to give you a typical, you know, sort of in the field example of where I've seen the effects of pressure affecting dew point is I visited a refinery one time because they were having difficulty. The piping in a refinery is exposed to the ambient temperature. And they were reading -40 dew point on their hygrometer, which the instrument they were using to read dew point. Yet out in the field, instrumentation was freezing up. And the reason is because they were reading -40 at atmospheric pressure. So if you took that up to 100 pounds and went across, that would be around +10. Well, unfortunately, in the wintertime, we have lower temperatures than +10. So they were actually having condensation in their lines. And first it started with hydrate formation in the pipes and then freeze-ups. But the point is when you're measuring dew point, you have to actually determine whether you're measuring it at atmospheric pressure or line pressure. And it's always a good idea to check the hygrometer, the flow cell on the hygrometer, to make sure the valves are set to measure dew point at line pressure. The end result was, when we went and looked at the dryer in question, the reason it wasn't making -40 at line pressure is because someone had left the bypass open. So they weren't getting a good dew point downstream because they were bypassing the dryer.
Yeah, that's a good point, Russ. And, you know, Instruments Society of America, or ISA, they always recommend that the dew point is approximately 18 degrees Fahrenheit less than the lowest temperature that your piping will be exposed to. And that's just to assure that that there's no potential for condensation. We've worked on some applications for northern Alberta, where since the climate is so cold down there, they require dew points down to minus 60. Previously, I was talking about, you know, don't fill your tires up with, you know, warm, humid air. Similar application we worked on, or I had the pleasure of working with Russ on, is they actually installed air dryers to lower the dew point down to minus 60 for specifically tire inflation. And that would just assure that when they're working in their cold climate with those monster tires or monster trucks, there would be no potential for ice formation or condensation, and it just makes everything work better. Yeah, as previously I stated, you know, some of the contaminants that I'm elaborating on consists of water. Even though we may not see water as a contaminant, in compressed air it is. The other contaminants is oil, and water and oil can exist in the form of vapor, aerosols, or liquids. You know, the other contaminants in compressed air are particulates. It could be rust scale, pipe scale, dust, anything that the compressor introduces into the compressed air system. This little indication or this visual presentation shows that, you know, we get the oil from oil lubricated compressors, but in reality, being in big cities or locations where there's hydrocarbons, when you compress atmospheric air, and if you're near a highway or something, there's a certain level of hydrocarbons from the pollutants, and you would still get a certain amount of oil vapor or contaminants, hydrocarbons, just due to the pollution that exists in municipalities. So even though you may think that you're getting oil-free or clean air, in certain circumstances, we would still recommend either carbon towers or something to polish off any additional hydrocarbons from the compressed air system, even though you have an oil-free compressor. You know, what are the consequences, or why do we want to purify our compressed air? You know, we want to prevent erosion, corrosion, freezing, product contamination. That all occurs due to the contaminants in the compressed air system. It could be due to the liquids, water vapors, you know, chemical contamination. And when you compress the air, it's all increased by 7-fold. Oh, Russ, you were saying that some of the consequences of corrosion, was it corrosion or erosion? I always get the two mixed up.
Well, they're kind of married in a way, because you know, if you have corrosion in your compressed air lines, and you have particulate, the particulate is going to fly down the pipe at extremely high speeds. So if there are elbows or changes of direction, or you have to pass through valves, things like that, this particulate load actually multiplies itself as it flies down the pipeline, because it erodes pieces of the pipe. So what you have is this big particulate load flying down to your application, whereby, you know, possibly you have filters on the pipeline, but they're going to load up fairly quickly with this contaminant and cause a lot of pressure drop, which equals harder work for the compressor, which equals, you know, more energy costs. So, but, you know, the corrosion-erosion relationship kind of goes together, and it's one of the ones that I see quite often causing people significant problems in the plant.
Yeah, good point. You know, Russ, just looking at this slide again, it indicates potential health hazards, and I always like to bring up the scenario. This one correlates chemical gases with potential health hazards, but similarly, just having liquids or moisture in your compressed air system can also, cause potential health hazards. And we'll see this a bit further down in future slides. But, all hospitals have compressed air purification systems. All dentists have compressed air purification systems, just to assure that the moisture content is so low in the air lines that there'll be no bacterial growth. So I think we should put a check mark also in liquid water for potential health hazards on the future presentation, because it's not only caused by chemical gases. Yeah.
Good point.
This rule of thumb is that for every 20 degrees Fahrenheit that we increase the temperature, we double the moisture holding capacity that air can hold from a vapor form and then into a liquid form. Or inversely, if we decrease the temperature 20 degrees, it can hold half of the moisture holding capacity. So basically what I'm trying to elaborate here is that if you drop the temperature down by 20 degrees, then those vapors will condensate and turn into a liquid form. So the 20-degree factor is the maximum holding capacity in a vapor form that the air can hold. And it's a bit better illustrated on the following slide. On this slide, we see that at 100 degrees Fahrenheit, the maximum vapor holding capacity of air, and not only compressed air, but just general air, would be 21 grains at 100 degrees Fahrenheit. If we were to lower the temperature down to 80 degrees Fahrenheit, it would be only 11 approximately grains per cubic foot would be the maximum holding capacity. So if your dew point was 80 degrees Fahrenheit and your actual temperature is 100 degrees Fahrenheit, you would basically have a 50% relative humidity in your air because you're at approximately 50%. Yeah, relative humidity, is always expressed in percentage, and it's relative to the temperature of how much moisture the air can hold. So relative humidity will always have the maximum holding temperature, and then if your dew point is 80 degrees Fahrenheit as previously shown, you would have approximately 50% relative humidity. And it's a bit clear stated on this slide here. And what I tried to indicate here is if your maximum capacity is at 100 degrees Fahrenheit, 21 grains per cubic foot, and your actual dew point is 80 degrees Fahrenheit, you would have a 52% relative humidity. Similarly, if your maximum capacity or your airline temperature is 80 degrees Fahrenheit and your dew point is 60 degrees Fahrenheit, you again have a 52% relative humidity. But in reality, what we're seeing here is that even though the relative humidity is the same, at 60 degrees Fahrenheit, I have approximately 1/4 of the moisture content compared to the 100 degrees Fahrenheit. So if I had a dew point of 60 degrees Fahrenheit and my air temperature was 100 degrees Fahrenheit, my relative humidity would be approximately 26%. So the point is that it's always relative to the maximum holding temperature, and that's what it's relative to. And this illustration is just to show you again that for every 20 degrees we decrease the temperature, we lower the moisture holding capacity approximately in half. So at 100 degrees, we have 21 grains per cubic foot. At 80 degrees, we have approximately 11 grains per cubic foot. And that's why it's sort of important when you were sizing compressed air systems. We always try from a performance standpoint to get the air, or we recommend that the air is as cool and as dry as possible. But a bit further, we'll see, in reality, we have to size it for worst case conditions. initially I was talking more about, moisture and water and the consequences, but one of the negative consequences in the compressed air system is a lot of times we have oil lubricated compressors. And again, our goal is always to get the temperature down as low as possible so that we can change those vapors. We can change the vapors into a liquid form, and the liquid is a lot easier to filter out, or the contaminants are easier to filter out in a liquid form compared to in a vapor form. So this illustration is just showing us that at 100 degrees Fahrenheit, we have approximately 0.62 ppm of oil in a vapor form. If our temperature was 150 degrees Fahrenheit, we would have approximately 5.8 or approximately 8 times more oil vapor. So it's a lot more cost effective to filter out oils or do filtration when the contaminant is in the liquid form compared to when it is in the vapor form. And that's why our goal is to try to get the temperatures down as low as possible to get that transition from a vapor into a liquid. Yeah, here's an example of a typically sized purification system. And again, we're elaborating on the consequences of temperature versus flow capacity of a compressed air dryer. So here we're illustrating a compressed air dryer that has a capacity of approximately, sorry about that. It has a capacity of approximately 3,800 SCFM at 100 degrees Fahrenheit, would only have a capacity of 2,157 SCFM at 120 degrees Fahrenheit. So it's not exactly half the capacity, but it has a substantial negative consequence by operating your compressed air system at elevated temperatures. And again, it's just due to that we haven't changed those vapors into a liquid form and removed them in a more efficient way. The following slide shows us the same consequence, but when we're operating at 100 psi and what the capacity consequences of operating at a lower pressure. So at 100 psi, illustrated again, we have 3,800 SCFM capacity. If we were operating at 85 psi, the capacity would go down to approximately 3,293. It's just that the more you compress the air, the more that those vapors turn into a liquid form, and the more that you can knock them out in the liquid form.
So Zenon, when sometimes when I'm talking to a customer and they give me flow conditions, we're starting to see how important it is to not only have the flow that they expect to see or the flow of air that they want to dry, but it's also important, as these charts illustrate, that we find out exactly what the inlet pressure range is, right? And exactly what the inlet temperature range is. So to give you an example, if I'm talking to a customer that tells me, oh, I have 1,000 SCFM at 100 PSI and 100 degrees F, I always want to investigate that further and get a range on the temperatures, because as you can see, just using this chart, if you size a dryer for 3,800 SCFM at 100 PSI, and it got installed in the plant, and there were certain times of the day when the demand in the plant was very high, and the pressure fell to 90 PSIG, that dryer, if it was sized on 90 PSIG, it would be undersized. So it's very important that we get a range. The dryers are sized with extra capacity, but it's a good idea to have this range. And what we want to find out is the highest flow, the lowest expected pressure, and the highest expected temperature. Those three factors will give us what we would term the worst conditions. And it may only happen for a week during the year, but the dryer is able to tailor its energy usage if the worst conditions are not present. In other words, it'll save the energy if the moisture load is reduced, for example, in the winter time or during nighttime when the demand on a compressed air system may not be as high. But these two charts illustrate why it's important to find out lowest expected pressure, highest expected temperature, highest expected flow. That way, whatever dryer you size will always make dew point 24/7. Sorry to interrupt.
Yeah, no, good point, Russ. And it just makes me think of some of the installations we have at various locations. And in the summertime, they're working at their worst operating conditions because the temperatures are high. Pressures could be low in certain circumstances if they're running full flow. And so we see, many installations which the unit is working at its maximum capacity just due to the climatic conditions in the summertime, and then in the wintertime, just due to the ambient dew point or the moisture in the ambient air is so low that the dryers or the cycle. So we'll get into this on the future presentations, but some of these units operating on a 4-hour cycle for regeneration or for regeneration of the desk and beds would go to a 24-hour cycle just due to the moisture content in the ambient air is so much drier in the winter time. And Russ, I don't know if now's the time, but I was going to elaborate a little bit on the importance of a good moisture sensing system, because as you stated, these units are sized to operating at worst case conditions, but rarely do the actual units operating at the worst case conditions. So it's sort of critical that there is a very reliable sensing method to determine when the dryer is not operating at full flow conditions or when the moisture content is less. But we'll save that for the next presentation. Yeah,
that's a good point. It's just compressed air is one of the most expensive utilities in the plant. So, when you're drying compressed air, the cost of drying the air or regenerating whatever type of dryer you have becomes significant. So if there isn't some type of device or method on the dryer to monitor the moisture load coming to the dryer, which will change based on the seasons, based on the flow, based on the temperature and pressure, then you're going to be spending money needlessly. And with the electrical rates where they are right now, every plant is trying to reduce its electricity consumption. So it's very important when people look at compressed air systems to determine, these flows and conditions and try and save as much energy as possible. And that might determine the type of dryer they actually select in the quotation process. But like you say, we'll cover that in the next seminar.
Yeah, on this illustration is just showing some real life conditions. We've indicated that we want to get the dew points down, or we want to assure that there is no liquid formation. And this is just indicating what is the consequence if you have high relative humidities. So as Russ previously stated, if there's corrosion, erosion that occurs, and with carbon steel, if your relative humidity is 2% or higher, then you get the corrosion or pitting of carbon steel piping. So you want to get that down as low as possible. For medical, dental, food industry, we want to get, or we have to guarantee that there is no bacterial growth. So the relative humidity has to be below 10%. In the market, there's typically most popular two designs of compressed air purification systems, and they consist of desk and dryers and refrigerant dryers. Desk and dryers can get your dew points down to -40 Celsius. We also, there also exists units that get it down to a -100 Fahrenheit dew point, or somewhere around -70 Celsius dew points for critical applications. Limitations of refrigerant dryers is that they can't go down below 4 degrees Celsius or approximately 38 degrees Fahrenheit, just due to their design. And as illustrated, with a refrigerant dryer, your relative humidity at 21 degrees Celsius would be approximately 31% relative humidity. With the desiccant dryer, you're down to 0.5% relative humidity, so you're below the threshold or the requirements of what is required for metallurgical protection and bacterial growth. Yeah, I've talked about ambient air, what happens when it's compressed, and we don't see the moisture, but here's a depiction of a typical compressed air system. And as previously stated, we take ambient air, goes through a air intake filter. It's in a vapor form. We don't see the moisture. Gets compressed, goes up to 100 psi or so. Consequence of compressing the air temperature could go up to 300, 350 degrees Fahrenheit. So then we want to modify or change, reduce the temperature down from 350 degrees Fahrenheit down to approximately 70 degrees Fahrenheit. So we would have water-cooled aftercoolers. The goal behind that, again, is to change the water from a vapor state into a liquid state, and then it would be removed by a mechanical separator. The mechanical separator would have a drain valve knocking out the liquids. Then in certain circumstances, we would have a air receiver. Air receivers are sort of important to have to prevent the modulation of the compressor, so it's not kicking in, kicking out on a regular basis. This way it would load, unload after a certain amount of time. And again, it's just another knockout pod to remove any liquids. Where we get involved is in this dotted quadrant, and basically that's our forte. So we start with the coalescing pre-filter, and that's your sort of last line of defense to assure that there's no more liquids that enter into the compressed air dryers. Compressed air dryers, or these desiccant units, are typically made only to remove vapors. And we want to assure that the coalescing pre-filter removes all liquid oil and liquid water. Liquid oil is somewhat detrimental to desiccant dryers, and that's another reason we always indicate that we want to get the temperature down as low as possible to convert those oil vapors into a liquid, and then they're removed with the coalescing filter. In certain industries, they require no hydrocarbons. So even if you had an oil-free compressor, there's still hydrocarbons in the atmospheric air. For electronic industry or certain food industry, they would still install a carbon tower, which would remove any residual hydrocarbons. And then the last item, now since your air is dry, hydrocarbon-free, you just want to make sure that there's no particulate matter going downstream into your instrumentation or into the application that you're using the compressed air for. So this is a typical, layout of a compressed air system consisting of all the components.
Zenon?
Yeah?
Go ahead. I was just going to ask you if you had a diagram of the refrigerant dryer, and there it is.
Yeah. So this is a typical depiction of a refrigerant dryer, and what was previously shown in the dotted lines consisted of the pre-filter and the desiccant dryer. It would be similar scenario here. You may have a pre-filter here just to assure that liquid droplets are removed and there's less chance of fouling on your heat exchangers. But the general operational aspect of this unit is you have wet saturated air coming in, goes through an air-to-air heat exchanger, drops the temperature down to approximately 70 degrees Fahrenheit. So uses some of the energy from the cold air coming out to pre-cool the air coming in. And then it goes into a freon to air heat exchanger. This would bring down the temperature down to approximately 35 degrees Fahrenheit or 3-4 degrees Celsius. Since now we've cooled the air down as far as we can cool it down, we can't cool it down any further than 35 degrees Fahrenheit, or else there would be freeze up that would occur if you brought it down below the freezing point. So that's the limitation of a refrigerant dryer. We've condensated all those vapors into a liquid form, and then it goes through like a mechanical separator, which is sort of illustrated over here. And this would knock out the liquid droplets, and then it's still at approximately 35 degrees Fahrenheit. And then we reheat, or we take advantage of that cold air coming out to pre-cool the warm air coming in. So it just makes it more energy efficient by using that lost energy or cold air going out to pre-cool the warm air coming in. So depending on the applications, you know, for certain circumstances, refrigerant dryers may be sufficient. From a capital cost, they're less expensive than the Deskin dryer, and from an operating cost, they're less expensive from an operating standpoint also. But they do have their limitations. That their dew point is approximately, you know, 35 degrees Fahrenheit versus a -40 dew point. So if you have any airlines going externally, this would not be sufficient. If you want to prevent bacterial growth, this would not be sufficient. You would have to go with a Deskin dryer.
Yes, and then just a point here. And I mean, our SPXFlow makes tens of thousands of these types of dryers worldwide every year. And they have, like you say, they have their specific applications that they're suited to. But the question that anyone who is looking at this type of dryer needs to ask themselves is, what processes do I have, or what equipment do I have downstream that is going to be compromised by liquids? And so to illustrate this, just to give you an idea, I once visited a factory where they had installed a brand new refrigerant type dryer, and all the piping in the plant was indoors. And so the customer was quite concerned because he had water in certain places of the plant. And he says, I don't understand why I have water. My ambient air is always 70 to 72 degrees, and my dew point from the refrigerant dryer is around plus 38 degrees F. I shouldn't have any condensation. The trouble is, though, is that the weak point in the system, I guess, is the separator, which you've shown at the side. And the separator is an inertial device. So there's a range in which that separator will have its highest efficiency at removing liquids. And because most plants have fluctuating demands for air, if you chart the air, you'll see it spikes at certain times and is lower at certain times. Well, if you go outside the range of this separator with your flow conditions, then the efficiency of it to remove liquids is going to fall off, and you may carry over liquid droplets downstream. So the example that I'm talking about, where I was in that plant, they had all kinds of fluctuating conditions, but the separator that was installed on the refrigerant dryer was only 90% efficient, even when it's in its optimum operating range. So if you consider that they were making, just for example, 10 gallons of condensate a day out of the evaporator, the separator was only taking out 9 of it, and a gallon a day was going downstream to end up someplace in the system. So this is why I always say to people, you know, if you're considering buying certain type of dryer, you have to ask yourself, where is water in my compressed air system going to cause me problems? Because if you can't have any water whatsoever, you can't have a refrigerant dryer. I mean, you can, but you're wasting your money. Does that make sense?
Russ, I was going to say that's a good point. You know, like typically those mechanical separators, they're rated at, you know, I think it's 10 micron, but it's 10 micron when they're working at their maximum velocity. So as the velocity goes down, that centrifugal force goes down. So then you're just letting more and more water droplets go through. And so instead of getting, let's say, as a stated 35 degree Fahrenheit dew point, you might be getting a 40 or even higher degree Fahrenheit dew point, just because we're not properly, or it's not properly removing those water droplets out of the airstream at that separator location. Good point. And here we see, again, a typical dehydration system. And as previously stated, the last line of defense is this coalescing filter. Prior to this, we have like mechanical separators, we have the receiver. And one thing I didn't mention, which is, going to be following in our future presentations, is that the previous items are, or the downstream items are very dependent on the previous items. So if your mechanical separator is not knocking out the bulk liquids, then this will be overloaded. This is your last line of defense. It's the last location where there's a drain valve to remove actual liquids. Desk and dryers are not made for liquid removal. I'm not going to get too much into this because I see our time starting to run low, but as previously stated, we were elaborating on how the dew points change from atmospheric pressure to line pressure and vice versa. So just to give a quick resume, we have saturated air coming into a desk and dryer, goes through the desk and dryer, you get down to a -40 dew point coming out of it, and that would be sent to your after filter. But you have to do a backwash because these vessels alternate from vessel to vessel. And as previously stated, a -40 dew point at 100 psi is the same as the -70 dew point at atmospheric pressure. So we would expand that 100 psi air at this location, and then the air would become extremely dry, or drier than the moisture content on the desiccant, and it would strip the moisture off of the desiccant bed and would come out of the muffler. But this is just a little precursor to our future presentations, and that pretty much wraps up our webinar for today. Russ, is there anything else you'd like to add?
No, I just think that the main thing is that everybody has an understanding of how flow pressure, temperature, and how compression affects the amount of particulate, liquid, vapor that you're going to have to deal with downstream somehow before you use compressed air in pretty much any facility.
Okay. All right, thank you, Zenon and Russ. Now, in terms of the questions and answers, we do have a few questions that's being raised. So one of the questions is actually pertaining to the scope of both supply and expertise. So is air dryer something that John Brooks would be specifically just looking at, or would you be able to cover other items within that compressed air process?
We definitely cover compressed air dehydration from a refrigerant standpoint, desiccant standpoint, but also John Brooks. We handle and take care of atmospheric filtration. So we are multifaceted, if I can use that term. If you have chemical contamination in your ambient air systems, we have design engineers that work on those kind of applications to assure there are no chemical contaminants going into the compressor. So we do pre-compression filtration, we do after compression filtration. I'm hoping that's answering the question, but we pretty much do it all.
So I would say, Zenon, even in a broader statement, anything on that diagram on the compressed air system that shows some type of purification device, whether it's the inlet filter to the compressor, whether it's the separator, you have a division that makes receiver tanks, and then you have the complete air purification packages downstream. The only thing that I think would be safe to say that you don't do is compressors, although I stand to be corrected by someone.
Yeah, that's correct. Like we have our in-house pressure vessel fabrication facility, which is rated to ASME code. And so we custom make pressure vessels and
Okay, and we have a question by Lovelash. For metal-to-metal contact, lubrication reduces friction and carry away heat from contact points, reducing wear. Is this interaction similar in compressed airlines?
So I'd say yes. I don't know if it increases the heat aspect, but it definitely increases the corrosive aspect. So if there's any a liquid contact, then that would create erosion inside the pipelines. So we always try to minimize or eliminate any liquid contact in pipelines to prevent any erosion in, compressed air lines.
And the other way to look at it is, and I'm not sure if this is, I'm not sure I understand the question completely, but if you have oil downstream in the compressed air line, that will certainly inhibit corrosion, right? But the problem is most compressed air systems are trying to eliminate contaminants because of some application they have downstream. So to send oil downstream to inhibit corrosion is probably the wrong way to do it, because that oil is going to end up in the application. So if you were a pharmaceutical plant, for example, you wouldn't want oil going downstream. Or if you were an automotive plant, you wouldn't want oil going downstream, because you need to, if you have to paint cars, oil in the paint will cause a blemish on the car and they'll have to do rework. So you're always trying to remove all these contaminants prior to the applications. So subsequently, you're going to have dry air going through pipe, and if there's no oil present and there is liquids, you're going to have corrosion. But as the slides pointed out, if we get below a certain dew point level, you will inhibit corrosion as well as bacteria growth, mold growth, that type of thing.
Okay, great. Thank you. So we have a question by Alessandro. Can you please comment on ambient air intake temperature and how it affects power consumption of the compressor? Have you seen marked increases in efficiency if air intakes are retrofitted to pull the outside air, air from the building?
So in designing compressed air systems, it's always recommended, if you're taking air from an outside source, to put it on this shady side of the building. Basically, you get more cubic feet of compressed air when the air is cooler. There is beneficial aspects to taking air from the internals or from the inside of a building. But then there's the air conditioning cost, is, that air conditioning. So there's a balance of, the cost of cooling that air down versus, having water cooled after coolers downstream to lower the moisture content. So it's not a simple question as sort of indicated, but it is always recommended that the air intakes on any compressed air system should be obtained from the coolest or on the shady side of the building. Basically, that's a general rule of thumb.
The other thing I can add about intakes, Zenon, is when because you guys represent the Dollinger company, they always tell me, and I've seen this proven at a couple of steel plants in the area here, where if you have a compressor intake that's, let's say, 10 feet or outside the compressor room, but 5 feet off the ground, if you double the height of that intake, you'll cut the particulate load on the filter in half. So this is another way to, I don't know if that actually helps the compression, but it actually makes your filters last longer, because the particulate level, the higher you go in the air, is less than it is on the surface of the ground.
Yeah.
Okay, thank you. So another question by Arun Batra. For instrument air with minimum ambient air at -40 degrees Celsius, what is the recommended dew point temperature?
If the ambient air is minus
40.
Minus
Yep.
40 degrees Celsius, as per ISA standards, Instrument Society of America, if I'm not mistaken, they don't say it in Celsius, but their statement is that the dew point should be 18 degrees Fahrenheit below the lowest ambient temperature that the pipe is exposed to. So I just go by Instrument Society of America. But from our experience, that's what we typically see, like in the northern oil sands, the units that we've supplied in the past were like -60 degrees Celsius dew points. And I think that fulfills the ISA standards. Hey, Russ, you're going to comment?
No, I think you've answered it pretty well. I was just going to say minus 40 degrees Celsius and minus 40 degree F are exactly the same things. The two lines cross. So if you took 18 degrees F below minus 40, you've got, you know, minus 58. So minus 60, minus 70 degrees F is going to be fine. You know, and the other thing you can do is look at, I believe on the internet, you can look up the ASHRAE numbers for almost anywhere. That'll give you a range of what the temperatures are in the area. And if you have instrumentation that are exposed to atmospheric air year round, it's a good idea to make sure that you're 18 degrees below the lowest reported ambient.
And
right.
once you get to those dry levels, there's so little moisture left in the air lines. If you're 18 degrees below the lowest, if your dew point is 18 degrees below the lowest temperature exposed to, then you'll be more than fine, I would say. Yeah.
The other reason they have that number is because typically when you dry or purify the compressed air, it's done at point A. And in this case, the instrumentation might be 1,000 feet down the pipe at point B. So there is going to be some decay in dew point from the time you created this minus 100 or minus 60 degrees dew point to the point of use. So that's what that 18 degrees is for, is just to give you a little elbow room. But exactly like you say, there's so little moisture at this level that really a freeze up would only be caused if you had a drastic problem on the dryer back at point A. You might get a little hydrate formation inside the pipe, but that's about it. You're not going to block any pipes.
Yeah, because in theory, as previously stated, if your dew point is minus 40 and your ambient temperature is minus 40, then you would have 100% relative humidity. But at those low temperatures, there is so little moisture left in the air that it wouldn't appear in the liquid form. It would just be little ice crystals, but it would be a minimal amount. But as long as your dew point is less by those 18 degrees, that's a safe rule of thumb.
Mm-hmm. Okay, thank you. And we have one more question from the audience. We're running close to our time limit. So when is a aftercooler, when using an aftercooler, is it better to use glycol or city water? And to add to that as well, is it possible to use air as well for the aftercooler, or pre-cooler rather?
Yeah, typically on aftercoolers, you know, downstream of the compressor, as previously stated, you know, the temperature can go up to 300, 350 degrees Fahrenheit. If you can use an air-cooled aftercooler and it doesn't heat up your premises or wherever your compressor is, you know, I'd say that's the way to go, because air is pretty much free from that standpoint. It's just the cooling aspect. Water-cooled aftercoolers are more efficient. They take up less space. You know, if you have free city water, then take advantage of it. Otherwise, you know, a glycol system or a chiller would be able to bring the temperatures down lower, but then there's the energy cost associated with it. So from a operating cost standpoint, air-cooled aftercoolers are probably the cheapest to operate, but they won't bring the temperature down anywhere near to a water-cooled or a glycol-cooled application. So when we size our dryers or do design work, you know, we take into consideration the moisture load, and that would have a consequence on the selection of the equipment. So if you're getting the temperature down to 70 degrees Fahrenheit using a glycol system, then you may be able to reduce the size and the operating cost of your purification system, because you've knocked the moisture load down substantially by getting a cooler inlet temperature to the purification system. So it's multifaceted. You know, we would have to look at the actual operating cost. If it's a small unit, it might not be cost effective to have that extra equipment. If you're looking at larger equipment, then the payback for that additional cooling capacity may be cost effective, yes.
Okay, great. Thank you very much, Zenon and Russ. So out of respect of everyone's time commitment, we are past our time limit. So there are a couple other questions that we haven't responded to, but we will be responding it to in the follow-up email, which will also include the video link for this presentation. So again, thank you very much. We will be sending the invite for the next two webinars pertaining to air and compressed air purification. So again, thank you.
Hey, thank you. Thanks for organizing this, Nico.
Yep, my pleasure.